Okay, let's get started. So welcome everybody to this session on shampoo and hair conditioning products. We have a first long talk and then 4 short talks. The first one is by Tomer Koren on preconditioned stochastic tensor optimization.
Thanks. You kind of ruined my joke, but thanks. Okay, so I'm Tomer Koren from Google in Mountain View. I will present a joint work with Vinit Gupta and Yoram Zinger. And it's about a new algorithm for stochastic optimization over tensor variables. And the name shampoo will become clear. Why we call it shampoo will become clear in a second. Okay, so optimization in machine learning. It's 2018. How does it look like, basically, roughly speaking? Many problems in machine learning can be simply described as a minimization of some loss function. Let's say it's a loss function over a variables W in RD. And what we often do, in most cases, in almost all cases, we simply use gradient descent or more often stochastic gradient descent to update the parameter vector to solve this optimization problem. Here, GT is a gradient, more often a stochastic gradient of the loss function at the current iterate, and eta t is some choice of step size. Another very popular family of algorithms that is being used in practice are the so-called adaptive methods optimization algorithms, Adagrad, Adam, and so on and so forth. These are basically algorithms that they have an update rule for each individual weight, each individual entry in the weight vector. And so each entry has its own step size, which is adaptively updated using past gradients. So hence the name adaptive methods. And there are also momentum variants of these methods that are also, they have a slightly different update rule. And why this is roughly the picture? Because, we cannot afford more than linear time per step usually, and these are kind of the only methods that run in this runtime. Okay, so what else is there? So potentially more powerful family of algorithms are known as preconditioned algorithms, which are basically just algorithms that use some matrix called a preconditioner to transform the gradient before taking a step. Okay, so this family includes the algorithms I mentioned before. When the preconditioners are diagonal, we recover the previous algorithms, but they can be potentially more powerful if the matrix is not diagonal. And so we can get, for example, full Adagrad algorithm, natural gradient, and also classical algorithms like Newton method, quasi-Newton method, and so on and so forth. Now, it's well known in optimization in many different scenarios that preconditioning often leads to faster convergence, to better dependence on condition numbers. It kind of transforms the optimization landscape in a way to make it easier in some sense. But of course, it comes with some obvious caveats. The first one is that we need at least quadratic space in the dimension to just store the preconditioners. And often we also need cubic time to update it, the preconditioner, to invert it, to apply to the vector, to the gradient vector, and so on. So it's not very practical in general. And the obvious solutions are, as we mentioned before, to just use some diagonal approximation. So we can think about the diagonal methods as approximation of the full-blown algorithm. And often we just use SGD again. So the focus of my talk today, I want to focus on this trade-off between the full matrix case and the diagonal case. Can we make a balance between these two extreme cases? Can we find something in between that will be as powerful or nearly as powerful as the full matrix case, but we can use it in practice like the diagonal case? It will be in terms of storage and runtime. And I will present a new algorithm, shampoo, which is, you can think about it as a new adaptive preconditioning algorithm where the preconditioners are adaptive based on past gradients. It will be more expressive than just diagonal preconditioning. It will be practical to store and compute in practice in large scale. It comes with conversion guarantees, and it's very easy to deploy, to use in practice, and it actually gives very nice results. Okay. Before I get to the algorithm itself, I will just remark that the name shampoo has nothing to do with probably the world's most famous algorithm of how to wash your hair. Even though maybe in these days SGD is even more famous than this algorithm. It's called shampoo just because it's about preconditioning. Okay. So let's start with, let's derive the algorithm. So it is actually based on a general recipe for preconditioning that was the subject of our previous work from last year. And this recipe is actually pretty simple. It says that for obtaining some family of algorithms, one should just pick the preconditioner on time t as the minimizer over all positive definite matrices of some objective, which makes a balance between the dot product of the inverse of this preconditioner and the cumulative covariance matrix of the gradients observed so far, and some potential function of the preconditioner. Now, in this talk, I will just focus on one choice of this potential function, which is the trace, simply the trace of the preconditioner. And in this case, the minimization problem can be solved in closed form, and we get the algorithm known as Addergrad, which simply pick the preconditioner as the root of this cumulative covariance matrix. Okay. Now, of course, we cannot compute roots of huge matrices in practice in large scale. And I guess that the main idea here is to place some constraint that we can think about as a computational constraint on this minimization problem, so that we'll only optimize it, we'll only find preconditioners that are practical to use. So why solve this minimization problem over all positive definite matrices if we can't actually use them in practice? We can apply, multiply with this matrix. Let's search over just these matrices that we can actually use in large scale. Okay, so the obvious suspects, the obvious past suspects for this kind of constraints would be, a low rank, maybe perhaps low rank matrices, or very sparse matrices, or some combination of the two, or a sketching of the matrix, and so on and so forth. But remember that I'm looking for something practical, not just a poly-time efficient, but actually something that we can work with in practice. And our motivation for this specific constraint for the entire work comes, of course, from the motivation for optimization these days come essentially from training of neural networks. And in neural networks, each layer is naturally described as a matrix of variables. Let's say in this case, 100 by 500 matrix. And so the gradient with respect to these parameters is also naturally described as a matrix of the same size. Now, if we were to apply preconditioned algorithm to this kind of, to this optimization problem, to this variable specifically, the algorithm will just flatten out the parameters, form a huge vector of size 50,000 dimensions, and presumably will apply some huge preconditioner to this vector. Now, this is not practical, as I said, but here is something that we can do. We can retain the structure of the matrix structure, or more generally, the tensor structure of the gradient, capital GT here, and precondition it using two much smaller matrices, LT and RT here. Okay, so our LT is just 100 by 100 matrix, RT is 500 by 500, and each of them is used to precondition either the rows or the columns of the matrix GT. Okay, this is something that we can do, and it kind of amounts to some form of some slightly weaker preconditioning than a full huge matrix. And of course, this matrix or tensor structure doesn't only show up in neural networks. It shows up in multi-class classification, matrix completion, and many other problems in machine learning, arises naturally. And of course, it's supported. It's a building block. It's a primitive in modern machine learning frameworks such as TensorFlow and architecture such as TPUs. So it's very practical to work with these kind of objects. Okay, so more explicitly, this kind of constraint mathematically is written as a Kronecker product constraint. So the constraint is that the precondition that we are looking for can be described as a Kronecker product of two smaller matrices, L and R. And while we cannot solve this exactly, this optimization problem exactly, we can prove a nice lemma that relates actually upper bounds in a metric sense the full Adagrad preconditioner, which is given here on the left side, upper bounds it using a Kronecker product of smaller much smaller matrices. So you can think about this first matrix as LT and this one as RT, and we have this mysterious fourth root exponent, 1/4 exponent that arises from the analysis here. And basically, this lemma immediately gives our algorithm. In the metrics case that I show here on this slide, it's very simple to describe. This is basically the whole algorithm. So here is the gradient in the matrix form, and we use two different matrices on the left and on the right to preconditioning. And the matrices are easy to compute on the fly, online. These are just cumulative sums of some products of the gradient with itself. And using the lemma that I showed at the last slide, we can prove, we can analyze this algorithm in full in the stochastic and online convex optimization framework. So we assume convexity here. And we can show in our regret analysis that the regret and hence the convergence rate of this algorithm can be described using the traces of these these matrices in the end of the execution. And you can think about this bound as kind of a data-dependent 1/√T convergence rate. In the worst case, it will be like 1/√T, but it can be faster if the data is well-behaved in some sense. And the nice feature is that if we have more structure in the problem in the sense of lower rank of the gradients, then we get better bound. So the better the structure, the more the structure, the better the bound. Of course, everything I said extends to higher order tensor. This is much more technical, and I'm not going to show anything in the slides. Please come to our poster to hear more. It extends to arbitrary tensors of arbitrary dimensions. And this full tensor version we implemented it in the TensorFlow. We now work on TPU support. Hopefully, it will be very soon open source under TensorFlow in GitHub. Now, I did say convex for the analysis, but in practice, we can just apply it to whatever we want, right? And of course, we will apply it to training some state-of-the-art models. I'll show here just two examples and give more details in the poster. So here we ran it on ResNet 55 model on C400, and this guy in the bottom is Shampoo. And I think the interesting thing is not actually appearing in the plot. The interesting thing is that while Shampoo is using a much more complicated update rule than SGD and Adagrad and related algorithms, in practice, the time per step when we run it on GPUs is very similar. It's only roughly 5% difference between SGD and this much more complicated algorithm. So this is actually quite nice. We also ran it on a different domain in language modeling, on a transformer architecture, on the LM1B data set. Here, the results are even, I would say, better. It gives a very nice speed up. So let me wrap up. So basically, we introduced a new adaptive preconditioning algorithm that you can think about as a practical approximation of the full matrix Adagrad algorithm, or ADAM. We have a similar version for ADAM. It's practical, scalable, it has convergence guarantees in the convex case, and it's very, very easy to use as a TensorFlow optimizer. So if you just want to check it on your favorite model, it's very, very easy to do. And as I said, TPU support is forthcoming, so hopefully it can work even faster. Our poster is number 68. Thank you very much for listening.
we have plenty of time for questions. Yes. Please use the microphone.
On the experiments, did you show training or test numbers?
Right, a good question. This one is for test perplexity. The previous one is just for training. For test, we see like a very strange phenomena. As it's not just unique to this algorithm. Basically, everything except SGD, we have some weird phenomena in test time. So this is just for train. And as I said, it's same phenomena appears in many other algorithms on CIFAR 100. For this one, it's impossible to overfit to the test set. So here, it's actually exactly the same. Train and tests are exactly the same.
Thank you.
Sure.
Okay, thank you for the valuable presentation. I didn't get the dependence on the dimensionality in each iteration. Could you give more explicit bound for that, please? Thank you.
So in my convergence bound, you did not get the dependence?
Yeah, in convergence bound.
Yeah. So the dependence on the dimension here, so we have a dependence on the rank of the matrix, which is in the worst case is D, right? But it can be lower. These terms can also depend on the dimension of the smaller matrices, on the size of the smaller matrices, in the worst case. But actually, in our experiments, we actually checked how these things behave, and these are the trace is actually much smaller than the dimension in most cases. So theoretically, we cannot prove yet anything like it, but it seems that in practice, it's better than just the worst case.
Okay, thank you.
Are there any more questions? Okay, then let's thank the speaker again for a nice talk.
Thank you. That's yours.
Okay, our next speaker is going to be Surya Guanasekar. She's going to speak about implicit bias in optimization geometry.
Thank you. Good afternoon, everyone. I'm Surya. I'll be talking about our work on characterizing the implicit bias of optimization in terms of the geometry of the updates. This is joint work with Jason Lee at USC, Daniel Suti at Technion, and Nati Srebro at TTI Chicago. So let's look at a simple linear regression problem where we have n training examples of pairs of inputs and labels y, and we want to learn a linear predictor, which is d-dimensional, by minimizing a squared loss over the observed examples. We'll particularly be looking at an over-parameterized or underdetermined system where the number of parameters we want to estimate is much higher than the number of examples we have. And in this case, the optimization objective as written here is ill-posed. There are many W which perfectly fit the training data. And as a consequence, we have many W which are global minima of this problem. So for this, I shouldn't be solving this problem. But if I did solve this problem with multiple optimization algorithms, different algorithms will take me to different solutions. So the question we want to answer is, like, which solution do we converge to if we optimize this objective with different algorithms? Different algorithms like gradient descent, stochastic gradient descent, etc. At least for gradient descent, when we have a very special characterization of which solution we converge to. In particular, if we start gradient descent with an initialization at W0, some W0, we can show that the updates eventually will converge to a solution which minimizes the distance to the initialization W0. In particular, if I initialize at 0, we'll converge to a minimum Euclidean norm solution. And this happens even though we never specified Euclidean norm in the training objective to begin with. Well, this might seem surprising if you haven't seen it before, but the proof is very simple. It's one line, which essentially follows from observing that the gradients are always spanned by the data matrix, the rows of the data matrix. So in other words, even though I have the flexibility to look at all solutions, my gradients take me in a particular manifold, which is n-dimensional, and within the n-dimensional manifold, there is a unique solution, which is the minimum norm solution. So this was simple. What happens for other algorithms? In particular, gradient descent can be looked at as special case of a broader class of algorithms, wherein in gradient descent we are working with Euclidean geometry. In particular, for mirror descent is a class of algorithms where we are minimizing a local approximation of the local linear approximation of the loss while constraining the updates to be close to the current iterate. And here the closeness is defined in terms of the Euclidean norm. And gradient descent can also be specified as a special case of steepest descent with respect to general norms, where we take an update step along a direction which has small correlation with gradients, but the norm of the updates are constrained to be unit norm. A generalization of this would be mirror descent with respect to a general convex potentials, where we do the same local linear approximation, but now the closeness to the current iterate is specified in terms of a Bregman divergence. And in terms of generalization of steepest descent, we again do the same thing, but the norm in which the updates are constrained to be is specified by a general norm. So the norm and the potential specifies the geometry of these updates. And the question is, can we relate the implicit bias of optimization for these problems in terms of the geometry of the updates? And in this paper, we provide some partial answers to these questions for the special case of linear models. And in particular, for linear models with squared laws, we show that when we do mirror descent with respect to general convex potentials, we converge to a solution which minimizes the divergence to the initialization, where the divergence is specified by the geometry psi, which is the potential of the update. And this holds for any step size, dual momentum, instance-wise stochasticity, et cetera. So this holds in a very robust way. On the other hand, for steepest descent with respect to general norms, the expected initialization does not hold. In other words, even in nicer settings where the norm square is strongly convex, or even if you take infinitesimally small step sizes, our intuition does not carry forward, and we don't get to a solution which is minimum norm to the initialization. So this particular problem has also been studied under a few different optimization algorithms. In particular, it has been studied under matrix factorization, so gradient descent on the matrix factorized space. You write the updates, the parameters you're estimating are matrix, and you write the matrix as in the factorized form and do gradient descent updates on the factors. And you can also look at this problem when we do adaptive gradient updates, such as AdaGrad. And for both these cases, it has been studied for squared laws, and there are some ideas on what the bias is, but it holds under very special conditions, and the characterization is also much more special. So what we have so far is some positive results for squared laws, and some places where we weren't able to give a useful characterization for what the implicit bias is. Now let's look at what happens for a different class of problems, which are differently ill-posed. In particular, we are looking at logistic regression on a linearly separable data set, where we are minimizing a logistic loss instead of squared loss. For this problem, the difference from squared loss is that this doesn't have any attainable global minima. In other words, on the other hand, you take any linear separator and scale the norm to infinity, and that would be a global minimizer of this problem. So it doesn't make sense to talk about minimum norm solutions here. Instead, what we can talk about is like which classifiers does gradient descent converge to, or in other words, which directions do these iterates converge to. And if you look at the gradient descent updates, we again have a similar characterization that it is spanned by the data. But here it doesn't make sense to talk about minimum norm solution. But it turns out that in terms of direction, we again converge to something very special. In particular, we converge to a max margin solution, which is also the support vector machine solution with hard margin constraints, where we are maximizing the margin of the closest data point subject to the norm of the classifier being 1 in the Euclidean norm sense. So here, not only is the form of the implicit bias different from squared laws, but we also have a characterization which is completely independent of initialization, W0. Okay? And okay, so now we can ask similar questions for other optimization algorithms, and it turns out that we can give a similar characterization for a broad class of optimization algorithms. In particular, the most interestingly, we also get characterization even when in squared law's case, we couldn't get a succinct or useful characterization. To just summarize, for gradient descent on logistic or softmax losses, we get to SVM solutions, which are hard margin SVM solutions for unit class or multi-class cases. And if you do steepest descent with respect to a general norm, we get to a solution which maximizes the margin while constraining the norm of the gradient in norm of the classifier in the norm of the updates we performing. Okay. And similarly, we get a very succinct characterization for matrix factorization problems too, where we have a bias towards nuclear norm. On the other hand, for AdaGrad, even with exponential loss, we show that the limit direction is not easy to characterize. In particular, we show that even with the exponential loss with norms diverging to infinity, our final solution will depend on initial conditions. So what we have so far is like two broad classes of family of functions, or two broad categories of results, where in one case we have a solution with, we have losses with a unique solution. And in this case, we can characterize the implicit bias for certain category of optimization algorithms in terms of closeness to the initialization. On the other hand, we have these class of logistic loss type models where you are strictly decreasing in the norm. There's no finite attainable global minima. And in this case, we get a characterization in terms of the max margin solution of the corresponding problem, classification problem. At a big picture, why do we care about all these things? In general, when we have over-parameterized models, using different optimization algorithms lead you to different global minima, or in other words, they have different implicit biases. And this, in turn, affects generalization, which is what we care about in machine learning. Okay? So in some sense, if you are using over-parameterized models, we want to understand what is the connection between optimization and which global minima we converge to, because that in turn specifies what is the inductive bias of the model. And while in linear regression setting, it's not common to have over-parameterized models because we often use some form of regularization. Most modern deep learning architectures we use today work in this over-parameterized regime. In other words, they have the number of parameters we use in standard architectures are way higher than the number of samples we are learning from. But in spite of that, in spite of having many global minima, most of which will generalize poorly and are nonsensical, we get to solutions which are good by using local search. And this leads us to believe that the inductive bias of the learned model for these over-parameterized models not only comes from the model constraints, but also mostly comes from the bias from the optimization algorithm, where the optimization algorithm is potentially leading us to specific special global minima. I would like to conclude by saying that when we are working with over-parameterized models, or at least as long as we are working with over-parameterized models, the role of optimization in machine learning extends much beyond reaching a global minima of the optimization. And implicit regularization or implicit bias from the optimization plays a crucial role in learning these models. And if you want to understand what is happening with these more complicated models, we want to more rigorously try to understand what is the bias of individual algorithms for such models. Thank you. Thank you for your attention.
Questions? Just a quick question: if you add an explicit bias, explicit regularizer like L1 or L2, is that compatible?
So when we have an explicit regularization, the problem is no longer ill-posed. It becomes a unique solution. We get a unique solution. The interesting thing here is, like, even if we don't have an explicit regularization, we get to something interesting. And the reason we do it not to get an implicit regularization, but to understand the geometry of updates, because there are problems where we don't understand what explicit regularization to add.
Okay. Thank you. Okay, our next speaker is Celestine Dünner. She's going to speak about distributed optimization.
So hi everyone, thanks for being here. It's a pleasure to present our work on distributed second order optimization. This is joint work with my co-authors, Aurelia, Mathilde, and Thomas and Martin, who is chairing this session. So the main contribution of this work is a new distributed second order algorithm, which is inspired by trust region methods. So trust region methods are generally not used in distributed settings so far, but they are mostly used for optimizing convex optimization landscapes. So the main idea is that you have an iterative procedure, and at every iterate you define a local model to your objective, which is easy to optimize. And you decide that you trust this model within a local neighborhood of your iterate. And under this constraint, you then solve an optimization problem on this nice surrogate model, you find an update, and you go to the next iterate. Based on how well you were able to approximate your function, you then adjust the region within which you trust your model for the next iteration. And you proceed, adapt your radius until you converge. So that's the core idea of trust region methods. And in distributed learning, we consider a data parallel setting where you have the data distributed across multiple nodes in a cluster, for example. And you want to solve a global optimization problem. And this is in general also done via an iterative procedure. You define some local optimization tasks, which you solve on each node. You communicate the results to the others to synchronize the work, and so on. And this procedure can also be thought in the setting here on the left. So we say we have a surrogate to our objective in each iteration, and we want the surrogate to be separable over partitions. This is the constraint we pose on this function. And in each iteration, we define such a surrogate, and we adapt it based on how well it was able to approximate our function. So to be a bit more concrete, in our paper, we consider generalized linear models. So we have a smooth data-dependent loss term and a regularization term. The objective is convex. And, sorry, this was too fast. I wanted to have this slide. And I want to find a block-separable approximation to this objective. So the objective should be a sum over k optimization problems that we can locally solve on the nodes in parallel. And we want each of this term only depend on local data because it's too expensive to communicate. And as well as the shared information that we exchange. So how do we get this block separable surrogate? So we start from our function and we have G be separable by assumption, which holds for any norm regularizer. So this is a reasonable assumption. And for the smooth loss term, we use a second order approximation. So this is the standard Taylor expansion. The first term is constant. The second term nicely splits over partitions, which are the columns of the data matrix. But in the third term, we have some correlations. So we cannot just distribute this task among k workers. So this is a dense matrix, and what we do is we use a block separable approximation to this Hessian information. So with this matrix, we can now split the objective into k independent subproblems. What we do in addition is we add this trust region parameter sigma, or a trust parameter, which is there to compensate for the approximation error that we make by using only the block diagonal information. And this is the parameter which is adapted in the course of the algorithm in a trust region sense. So this is the scheme that we propose. So we initialize our model, and then in every iteration, we optimize our separable surrogate in parallel over the k workers. We aggregate or exchange the updates, and then we update our model and adjust the sigma parameter. And this is done as follows. So this is a standard approach from trust region methods. You get your update, and you check whether how the function decrease is related to the decrease you would expect you have on your model. So you compute this quantity, then you check whether you actually get a function decrease. If not, you discard your update. If yes, You apply it, and then you check how far off your model was, so whether it was overestimating or underestimating your objective, and you adjust the sigma parameter accordingly. This method we can derive nice convergence guarantees for general functions with general convex regularizers. We don't have any strong convexity constraint there. But for more details, I refer you to the paper or pass by the poster. I want to give a brief overview of our prior work. So part of this approach have already been explored. So there's this COCOA method, which was being proposed by Virginia Smith and co-authors and has been extended in many papers. So there they use a similar second-order approximation to the function. They also introduced the sigma parameter to compensate for approximation errors, but they do not use local second-order information. They approximate the local Hessian by global Hessian information, which is given by smoothness of f. And at the same time, the sigma parameter is constant. It's just a worst-case upper bound. Then there's a second approach by Li and Chang in 2017, where they use the same model than we do with the block diagonal Hessian information. However, they do not use an adaptive model. So they have this Hessian approximation, and then they use line search to find an appropriate step size and guarantee convergence. This is different to a trust region sense, where you a priori constrain your step size. You try to find an update within a ball, and you're not finding an update and then finding the best step size. And these methods, to the best of my knowledge, the last one is not able to give convergence guarantee for L1 regularized objectives, so they need strong convexity. So we can, in addition, give that to like practical benefits that I'll show on the next slide. So to wrap up, I have here some experimental comparison of our method, the adaptive distributed Newton method, to the two methods I've mentioned before, the LS stands for line search and the COCOA method. What I should mention here, this is training suboptimality as a function of time. All these algorithms have been re-implemented in C using MPI, so this should be a fair comparison. 3 points here that I would like to emphasize is the first one is our method seems to work well. It pays off to do all this costly adaptation step as a function of time, which is nice to see. And what we also see if you compare to COCOA is that we have that the local second order information is really useful, especially for logistic regression where your function is not a quadratic. That's the comparison between the red and the blue curve. And the third thing is in the figure in the middle, we see that on the KDDA data set, the line search method is not working well. So this can stuck because you have a non-adaptive model. Yeah, that's all I wanted to show. Please come to the poster if you're interested to learn more, and I'm happy to take some questions.
Hi, friends. Thanks for the talk. I was just curious about have you tested with many workers? Because here it was only 8 and...
No, we didn't go to a huge number of workers because the general rule for this kind of methods is don't use more than you have to. And the data set you see here on the right, that's the Critio data set. I mean, that's a terabyte data set. That's huge. So it fitted in the memory of 8 workers. That's why we used 8 workers.
Okay, thanks.
Okay, let's thank the speaker again. Our next speaker is Frank Jutzeler, and his talk will be on delay-tolerant proximal gradient methods, also for the distributed case.
Okay, thanks, Martin. So hello everyone, I'm Frank, and this is a joint work with my colleagues from Grenoble, Jerome and Massy, and our former student Constantine, who is now PhD in KAUST. So as you said, it's, the context is the same as the previous talk. It's basically distributed learning in a setup where instead of having one big global objective like when you see on the left with a lot of examples that we all consider through local losses like Convex and everything, we have, in fact, that the data is split into several chunks, like big M chunks. And so, obviously, the problem reformulates directly as a sum over all this chunk of some local functions that, in fact, correspond exactly to local empirical losses on this particular subset of the data. So while we know very well how to minimize something on the left, like for instance with popular variance radius stochastic gradient methods, there's still a little bit of work to do to be really able to tackle what's on the right when you cannot move your data and you want to minimize it over different computer, different architecture with communicating the less possible. So that's what I'm going to present today. So basically, one direct way to tackle this problem is to say, okay, we have a problem which is basically a sum of many smooth functions, like M smooth function, and a regularizer. So if I extend directly the well-known proximal gradient algorithm to this distributed context by a simple replicating trick on the variables, I get the algorithm here, where at each worker you perform a gradient step. And then the master combines all these new variables and takes the prox of it. So it's basically what you could see, like for instance in Spark, something that's exactly a mapping of your gradients and then a reduced step. Okay? And that's exactly the algorithm you see below. And in fact, we know very well how to analyze this because it's basically just proximal gradient. So there's nothing to do. You have, for instance, if all the local data attached terms are smooth and strongly convex, then you know that your algorithm is going to converge linearly with some factor here. And there's nothing to do to prove that because it's just proximal gradient, as I said. But now the problem is, in fact, what I've mentioned here is in the case where everything is synchronous. So at each time, each worker is performing a gradient step and then sends their variable to the master who sends back. So this is completely synchronous. And as some worker may have a lot of more data than others or have more limited capabilities, then you might not want that. You might want to use them more efficiently. So you want to introduce some asynchrony. And also your vector data might be large, so you might want to reduce the communication cost between the master and the worker. So that's something that we're going to tackle here, so both the asynchronous case and the limited communication case. So in order to deal with asynchronism, we have to define what is asynchrony, how we're going to handle it. And in fact, so we're going to say it like this. Our general asynchronous framework is to say, okay, we have one worker, he finishes computing, so he wakes up and he exchanges with the master, who sends back immediately some new point, and he starts computing from that. And so that's how we're going to state things here. So to describe what we're going to do something very stupid right now. We're going to extend it a bit later. We're going to say, okay, the master always wants to have a fixed combination of all the worker variables, not gradients, really variables. And in order to do that, then what the update a worker should send is basically what he has now computed minus what he had before. So that's what the worker will send to the master. And what are the computation of the workers where basically before we are doing proximal gradient, then here we are going to do exactly the same, proximal gradient, meaning that the worker is going to receive the average value here, make a prox on it, and then compute a gradient step and send back everything to the master. And so this gives this kind of algorithm, who is now a bit different because it's not a mapping and reducing anymore. It's not something like that. It's something like looks like if you were doing some MPI implementation, it's an asynchronous send and an asynchronous receive. So basically, the worker waits that worker sends him something, and then he answers. And why are we doing that? Meaning, why are we combining iterates rather than combining directly the gradients? Well, we found out that it's actually much more stable to do that. For instance, if we compare with the proximal incremental aggregated gradient, where you do basically the same thing as us, but instead of combining the iterates, you combine the gradients, then what you have is that inside the prox, you have a gradient descent on the average gradient, meaning on the average of the last received gradients for the workers, as we do, but you're descending from the last point you have, whereas in our work, we descend from the average of the points where these gradients were computed. And in fact, this shows a lot more stability, especially when your setup is a bit messed up and you have a lot of delays and everything. So that's the reason why we do such thing. And another interesting thing we found out is that there is a really simple way and really elegant way we find to analyze this kind of algorithm. It's by defining what we call an epoch sequence. An epoch sequence is to say, okay, we're gonna split the time into chunks, like consecutive chunks, and in each chunk, we want that each worker is contributing 2 times to the master. And in fact, this means that at the end of an epoch, then every point inside the epoch before has been processed at least once by all the masters. So we don't have a direct dependence between one epoch and the one before. And this enables us to provide a very simple and elegant result saying that, okay, if we have the same assumption as before, like strong convexity, smoothness, then we have exactly the same rate as before with a fixed step size the same as before, but not on the number of synchronous exchanges with the master, but just on the asynchronous epochs that we define here, which enables us to tackle the case where we have a long delays and everything on the fly. So just to show some really small comparison with synchronous case and PyAg on a cluster with 100 machines, we put 10% of the data in the first one, and we run it as it is. So it shows like encouraging performances. And I just spent 1 minute explaining how to reduce again the communication cost here. While in fact, instead of doing just one proximal gradient step, we show that our algorithm can be easily extended to do multiple proximal gradient steps at the workers, which means that we can go on and compute and compute and compute again on the local data. So the gain we have will be exponentially decreasing, but we still have some gain, but the compromise is that the epoch will get longer and longer. So we have really a compromise to find, that's what's shown in the picture, to find how many repetitions we can do. But as nothing's fixed in our theory, you can do basically whatever you want. So if you're interested in seeing more of that and to discuss extensions that, for instance, specifying the communication, I presented that in ISMP slide last week for those who were there. Thank you.
Thanks a lot. We have time for some questions. Thanks. Okay, otherwise let's thank Frank again. So we're moving to the last talk of this session, but then there will be a session right after. So this talk is going to be on straggler mitigation using coding theory, and the talk is given by Netanel.
Thank you, and thank you all for coming. I'm going to be talking today about techniques for straggler mitigation and distributed gradient descent. In particular, we're going to discuss two approaches, one of which takes tools from the theory of error-correcting codes, and the second one from the theory of graph theory. Even though our techniques apply in a much broader sense, for the sake of this talk, you can just have in mind the vanilla stochastic gradient descent, where we have started the zero model and update it using the gradients iteratively, each time on a fresh data set. The bottleneck in this algorithm is the computation of the gradients that are used to compute the empirical loss. But fortunately, this computation is very much parallelizable. You can do it separately for each point. Or you can separate your data set to n batches and compute the partial gradients on each one of them, and then aggregate them together to get the full gradient. So this is what we're going to do. We're going to distribute the training set to n worker nodes in this way. However, such systems are very much prone to the problem of stragglers. These are servers that are slow to respond or completely unavailable. In this talk, we're going to address the straggler issue by adding redundant computations in the following sense. Each worker is going to get d batches instead of just one. Here, d equals 2. It's going to compute the partial gradient on each one of these mini batches and transmit back to the master server a linear combination of those gradients according to some predetermined matrix of coefficients B. For example, the first row of B here is a half of 1. It corresponds to this linear combination of half times the first partial gradients plus 1 times the second partial gradients. And our goal is to design the matrix of coefficients B such that we will able to mitigate stragglers. For example, let's think that the third worker here is a straggler. What the master receives is these two linear combinations, which can be written as this matrix. This is a sub-matrix of the matrix of coefficients. We denoted it by B sub k. And this is the matrix of partial gradients that we denoted by M. What we wish to compute is the sum of the average of rows of this matrix M, which amounts to multiplying this matrix M from the left by the all ones vector and then dividing by N. What we need for that to happen is that for this construction of coefficient matrix B, every submatrix B sub k will have the all ones vector in its row span. If we will be able to obtain that, then by linear combinations of these two responses, we will be able to recover the full gradient. For example, if here we use the decoding vector 2, 1, we take this linear combination of these rows, we get the all ones vector, and therefore we can compute the full gradient. This problem was defined initially in this conference last year by Tendon et al. They established the fundamental trade-off where the replication factor D must be at least the number of stragglers S plus 1. They gave an explicit construction for a restricted set of parameters using just a repetition scheme. And they gave a randomized construction for all parameters that provides equality in this bound, but incurred high complexity due to the lack of structure. In this work, we have two aspects. First of all, we provide a deterministic construction that achieves the lower bound D equals S plus 1. And provides a better complexity of obtaining the decoding vector by using techniques from coding theory for different parameters, specifically Reed-Solomon and BCH codes. In addition, to break the barrier on the replication factor, we suggest to approximate the gradient in a sense that will be made clear in a couple of slides, and we provide matching constructions with a constant D using expander graphs. For the first part of our paper, the matrix of coefficients that we built has this form. The leftmost column here is a minimum weight code word in an error-correcting code C that has to satisfy a few conditions. First of all, it has to be of a certain dimension, it has to be cyclic, it has to be a maximum distance separable code and contain the word 1. Please accept my apology if I'm using too much coding theoretic jargon here. For the sake of I'm my time restrictions, I have no choice, but I will be happy to explain more offline. Anyway, using these properties and simply just the ABCs of coding theory about the dual codes, we're able to prove that indeed this matrix has the one vector in the span of every n minus s rows, and therefore can tolerate any s stragglers in the system. Such an error-correcting code C is obtained by using Reed-Solomon or the BCH techniques. They're usually used over finite fields, but for our purposes, they work just as well over the real or complex fields. That's the first part of our paper. The second part discusses the approximate computation of the gradient. Recall that we cannot have a replication factor less than the number of stragglers plus 1. But this bound assumed that we only wish to compute the gradient exactly. Of course, due to this stochastic nature of our application, we can settle for computing it approximately. Specifically, we want the L2 distance of the vector that we obtain from the all-ones vector that we indeed want to be some decreasing function in epsilon, decreasing in the number of stragglers, of course, hopefully. Hopefully it should be 0 if there are no stragglers. The tool we use to achieve that is expander graphs. In one sentence, these are graphs in the combinatorial sense that every large set of vertices is well connected to the remaining vertices in the graph, meaning there are no isolated sets of vertices. And a bit more formally, if you take the irregular graph, you define its adjacency matrix. This is a binary matrix that gets 1 for every edge and 0 else. You take its eigenvalues and define the parameter lambda g to be the maximum absolute value between the second and the last one. A graph will be said to be a good expander if this parameter is small in some sense. So our construction in the case of the approximate gradient is as follows. It's pretty simple. We take this matrix of coefficients, normalized adjacency matrix of a good expander. The decoding vector in this case will be a carefully chosen yet very simple vector that can be obtained in linear time. Therefore, we have linear decoding. The replication factor here will be exactly the degree of the graph. And we're able to prove rigorously that the L2 distance between the vector that we achieve and the vectors we want is upper bounded by the parameters of the graph, specifically lambda g times some function of n and s. In addition, we're also able to prove that whenever the basic theorem of d and s plus 1 does not hold, regardless of how you choose your coefficients, there will always be some set of stragglers k that will spoil your party and gives you at least this much deviance in L2 norm from what you want to achieve. By using the so-called Alon-Bopana theorem, we can take the constructions and the converse and show that this construction is in case optimal if you use the best expanders that you have that are known as Ramanujan graphs. And this happens asymptotically when n is large and s is asymptotically less than n. Okay, if you would like to hear more, I encourage you to ask me offline or come visit me in Poster 221 today. Or there's a follow-up work to this work that takes a different approach and achieves very interesting results. You can simply Google Lagrange coded computing and see for yourself. I hope to see you today in the poster session, and thank you for your attention.
Is there a question? If not, I'd like to thank all the speakers of the session. Again. So we're moving on to the next session on convex optimization number 4. We again have 5 exciting talks. The first long talk is going to be delivered by Jelena Konikolas on randomized block coordinate descent.
Hi, everyone. I am Jelena Diakonikolas. I will be talking about alternating randomized block coordinate descent. I'll tell you in a minute what that actually means. And this is joint work with my postdoc host at BU, Lorenzo Recchia. So let's get straight into it. The setting is unconstrained convex minimization. We have our vector of variables, and what we do is we fix a partition into n blocks. And now I'm showing here blocks of equal length, but they can have any length, really. And I will assume that we have access to two types of blocks, or two types of oracles. The first oracle is the standard gradient oracle, to which we can feed a point and the block index, and we get a gradient over the coordinates from that block. The other type of oracle is a minimization oracle. So we feed it the same information, but now what we can get back is the minimizer of the function over the block. So here we do minimization only over this fixed block, and all other coordinates are fixed. And this may sound like a lot to ask, but it's not really. And we provide details in the paper where this is actually not expensive at all. Now, to talk about the problem, I need a few assumptions here. The first assumption is that my function is differentiable and I'll smooth the cell, maybe even infinity. I'll tell you in a minute. I will also assume that each of my blocks is Li smooth, meaning if I only move over one block, my gradient over that same block does not change too much. And now I'll isolate one special block. Without loss of generality, I'll assume it's the last one. And I'll assume that that block has the maximum smoothness parameter. So this block will be the worst one. And its smoothness parameter can be as large as infinity. And note that if it is infinity, then my function is, in fact, not smooth. It has some structured non-smoothness. Now, let me remind you what basic non-accelerated methods do. First, the cyclic block coordinate descent. This is almost a folklore method. I'm not even sure who to attribute it to. What it does, it fixes some permutation of the blocks. And in each time step, we either do exact minimization. That would be sort of the standard variant of this method. But you could also do a gradient step instead. There's analysis for that, too. So you know, what the method does is we have this example order. In every step, we select one of the blocks and do one step. What I want to bring your attention to is how the optimality gap depends on the smoothness parameters. These may be fairly complicated expressions, but what I want to point out is that there is dependence on all the smoothness parameters. So if one block was non-smooth, we would have essentially no guarantee. Now, if we look into a related method, which you can think of even as a special case of the previous method where we only have two blocks, it is known as alternating minimization. So here we would typically do exact minimization over both blocks. And so what we do is just we alternate in every iterations between selecting one of the two blocks and doing exact minimization. Now here's something really interesting. If you look at the dependence on the optimality gap in terms of smoothness parameters, you pay for the minimum. So you don't pay for one of the blocks at all. And now there is a third type of the methods, known as randomized block coordinate descent, introduced by Nesterov. So here what we do is we fix some probability distribution over the blocks. And the way we do our steps in a standard variant, we would be doing gradient steps. The analysis also works if you do exact minimization. So the method at each time instant, it picks a coordinate, it randomly samples it with replacement, and it does a step over one block. And here, our dependence on the optimality gap will be similar as in the first method in the sense that there is dependence on all the smoothness parameters. So to just wrap up about these standard methods, what happens here is that if we are dealing with more than 2 blocks, the standard methods pay for the smoothness of all the blocks. But that's not true for alternating minimization, which only operates on 2 blocks. There we pay for the minimum. And a natural question to ask is the setting of 2 blocks special? Or can we still get away with not paying for 1 block when there are more than 2 blocks? And this was also posed as an open problem by Becca and Tetrashvili, who were looking in the case of cyclic block coordinate descent. And this is what this talk is about. So let's see. The way we answer this question is by introducing a new method that we call alternating randomized block coordinate descent. And this method does not pay for one of the blocks. What the method does is it fixes a probability distribution over the first n-1 blocks. These are the good blocks. And then it does a gradient step over the selected block. And then in the same iteration, right after, it does exact minimization over the bad block. So here is the method. We sample randomly one of the first 3 blocks, and we immediately follow with the bad last block. Right. So I hope this is clear enough. So now we have 2 steps per iteration, 1 over a randomly sampled block, 1 over a bad block. Now, this method is related to the methods I talked about before. In fact, if we had only 2 blocks, we would be exactly doing alternating minimization. If there was no special block, we would be doing randomized block coordinate descent. So in some sense, we are interpolating between alternating minimization and randomized block coordinate descent. Something amazing happens here, and that is that we do not pay for a bad block at all anymore. What's even more interesting is that a method like this one is possible to accelerate. And if we accelerate it, we get essentially the best known convergence time in this setting, except that we don't pay for 1 bad block at all. Let me tell you a few words about how we analyze this without getting into too many details. So the convergence analysis is an extension of an approximate duality gap technique that Lorenzo Recchia and I have developed, and it applies to a very broad class of first-order methods. We originally developed it for full gradient methods, but in this work we have actually also extended it to the setting of block coordinate descent methods. So the main idea is as follows. So we want to minimize a convex function. When we have a single point, even if we know the function value alone doesn't tell us anything about how far we are from the optimum, because we don't necessarily know what the minimum function value is. What really gives us information is the optimality gap, the difference of the two. Now, because we don't necessarily know the minimum function value, instead what we do is we construct a certain lower bound that we can, in fact, evaluate. And this lower bound is also useful to be coupled with a certain upper bound on the function value of our running solution. So the difference of the two gives us a notion of an approximate optimality gap. In the way we construct it, and I won't talk about it here, it actually also has an interpretation of duality, which is why we call it approximate duality gap technique. Now, for this construction, our true distance to the optimum is upper bounded by this gap estimate. And the way we prove convergence is by trying to find some increasing function of the iteration count called AK. This AK is what determines how fast we converge. It is essentially our convergence rate. What we want to show is that this rate function times the gap is a non-increasing function modulo some small error. If we show something like that, we immediately get a convergence bound from here, because we have the decrease from the initial gap by a factor AK. And now, if this error is small enough, if it is convergent and it scales similarly as this initial gap, then the whole thing, the whole distance to the optimum would be decreasing at rate 1 over AK. What happens in the convergence analysis of the method I mentioned is that when we are constructing the lower bound, we use the function's convexity, the definition of the first order convexity, which gives us a lower bounding hyperplane on our convex function. Now, when we write this, we can also split this inner product over our n blocks. But what happens here when we do exact minimization over the nth block is that it does not appear in this lower bound anymore, because this is unconstrained minimization. We did exact minimization over the nth block, so the gradient over the nth block is 0. This should be gradient at 10. On the upper bound side, at least for the non-accelerated version, we use the progress that comes from a block gradient descent step. And the standard guarantee is that we can get some decrease over block I. But now we can actually, because in the lower bound, the nth block does not appear at all, what happens on the upper bound side is that we can only sample good blocks. And what happens is that we can completely drop the bad block from the analysis. If you want to get more information about how the analysis works, please ask me more also at the poster session. Now, let me just quickly show you a few experiments. What we did for the numerical experiments is a linear regression on a blog feedback data set. So what we show here first for the non-accelerated methods, on the top is the distribution of the smoothness parameters over blocks. This is for blocks of size 5. The methods I'm comparing against here, so our method is this navy one. The other two methods are randomized block coordinate descent and cyclic block coordinate descent. This G in the name means that when these methods are run doing only gradient descent steps, otherwise they all do exact minimization on the bad block. So this exact minimization on the bad block actually helps all methods, but what we can see here is the proposed method actually operates better. If you're too quick to point out, yes, but I was doing 2 steps per iteration, these experiments actually, in these experiments, we slowed down our method by a factor of 2. So we are counting 1 iteration as 2, and it is still faster. Here are the graphs for just a different block size. This is block of size 10, and you can see a similar phenomenon. And similarly for blocks of size 20. Here, the randomized block coordinate descent that does exact minimization is actually very close to our method, but it makes a large initial progress and then stagnates, whereas our method keeps making progress. I should mention that all these different lines, they are for 50 repeated runs, and then the bold lines are just the median. For the accelerated methods, we see even more benefits. So here we were comparing against different state-of-the-art methods. ABCGD is the accelerated cyclic block coordinate descent. NU-ACDM is the accelerated method with non-uniform sampling, and APCG does uniform sampling. So NU-ACDM is the closest to our method, but we can see that our method actually converges faster. Similarly, as for the non-accelerated method, we slowed it down to make the comparison fair. And now for different sizes of blocks, we see also a similar phenomenon, and actually for 20 blocks, we see a very, very high improvement. Now to summarize, what I talked about is new block coordinate descent methods that can get away with not paying for one bad block, no matter how bad that block is, even if it is completely non-smooth. This method outperforms existing methods if indeed our data set is such that we have one bad block. Now, some of the work I'm doing at the moment is extending this to some other settings. What I talked about was assume that the function was only smooth. I'm looking into settings where the function is both smooth and strongly convex, and I'm also looking at the composite non-smooth setting. And at the same time, I'm trying to get some improved bounds for randomized BCD, which we saw in the experiment also does better if it can do exact minimization. One open question I have here is, these methods I talked about, they can be slower by a factor 1.5 for the accelerated and factor 2 for non-accelerated methods if all the blocks are about the same. If their smoothness parameters are about the same. And what I'm wondering about is there a way to do uniformly better than all existing methods? Thank you. Please come to my poster. It is number 67, and I'll be happy to talk more about this. Thank you.
Are there any questions? We have some time.
Hey, thanks for the nice talk. I have a question. So you said your method is a factor 2 slower than uniform sampling over uniform distribution. Have you investigated whether you could generate a distribution of your data which is exactly fulfilling your property? Could you partition the data such that the average over n-1 smoothness?
So the sampling distribution was not uniform. You can actually choose it to be whatever you like. It is just going to give you different results in terms of convergence. And typically, what you would like to do is to sample proportional to the smoothness of a block. The reason it is slower by a factor of 2 is that the method actually does 2 steps per iteration, whereas other methods do only 1. Yeah. So in that case, it would do twice as much work, which means it's 2 times slower.
I just thought maybe you could construct a distribution where your method is beneficial, because you can ignore one block and on the rest you have better properties than if you would distribute uniformly.
Yeah, but that's something, again, that depends on the data set.
Yeah.
Sure. If the data set, if we can do these things and indeed one block is bad, yeah, then it's better. But if all the blocks look the same, then too bad.
Yeah. Okay.
Okay. Thank you for the question.
Okay. Many thanks to Jelena again for this nice talk. We'll actually see her again for the last talk. There are 3 more short talks, and the first of the short talks is going to be given by Nikita Doikov. and it's going to be on block cubic Newton methods.
Hi everyone, my name is Nikita Daykov, and I'm going to talk about randomized Newton method. This is a joint work with Peter Richtarik. So let me briefly remind how gradient descent and Newton method, a cubic Newton method works. So we want to solve, we want to minimize the function which is differentiable, and we assume that it has Lipschitz continuous gradients. Then we get the global upper bound for this function. And the minimum of this global upper bound will essentially give us the well-known gradient step. So now what about if you want to use second order method for our problem? One can try classical Newton method, but it's known that there is no proper global convergence guarantees for this method. Thus, we need to use cubic regularization. Now assumption a little bit different. We assume that the Hessian matrix is Lipschitz continuous. Then we get global upper bound, which now is the quadratic model of function plus qubit norm. And we minimize this global upper bound over the whole space. Okay, so what about complexity of these two methods? We want to solve the problem up to epsilon accuracy, and the question is how many iterations do we need to do? And it's known that for convex function, it's enough to do about 1 over epsilon iterations for gradient descent and 1 over square root of epsilon for cubic Newton, which is, of course, much faster. But we do not forget about the complexity of every step. And of course, for Newton method, the step of every iteration is much more expensive. Moreover, the linear dependence on the dimension of the problem is too high for modern applications. So we need to do something with that. And hopefully there is a technique which is called block coordinate methods, when we do on every step just update of a small number of coordinates. Thus, every step of such method is quite cheap. At the same time, we can prove similar rate of convergence for such methods. And this was the main motivation of our work, since there are a lot of block coordinate first order methods. There are no too much results on second order methods. And our aim was to create a second order method with a low cost of every iterations, but with a global complexity guarantees. So now let us try to look at our assumptions. Firstly, we have a special assumption about our problem structure. We say that our function is represented as a sum of twice differentiable and differentiable components. And let us say that we have some fixed block decomposition of our space. So our variable can be represented as a concatenation of small subvariables. And we assume that the twice differentiable component is block separable, which means that phi can be represented as a sum of twice differentiable functions. Every depends on its own set of coordinates. Okay? And for G, we do not assume any block separability. Thus, we get the following problem. We want to minimize the function, which is a sum of two terms. The first is a sum of block separable twice differentiable terms, and the second is one differentiable term. And we already kind of know natural assumptions, natural smoothness assumptions that we should apply. So we say that all the second order components have Lipschitz continuous Hessians, and G is differentiable, and yeah, we assume something which is quite general. So we say that G is upper bounded by linear model plus quadratic, and upper bounded and lower bounded by this quadratic model. So let us consider the case when G equals to 0 and A is identity matrix multiplied by L. Then this is a standard class of convex functions with Lipschitz continuous gradients. Another opposite case is when these matrices are the same, then G is just a quadratic function. And we added also set Q in our setting, but we assume that this is a simple set, so we can project into it. Now we have this function which we want to minimize, and it's already clear which is a proper model for this function from our smoothness assumptions. But we need to remember that we want to update only a small number of components per step. Thus, let us fix a set of blocks. So this set S is a set of components which we are going to update. And just a notation for vector Y. We say ys is a vector of the same length, but with non-zero components whose indices are in S, and all other components are 0. So we want to build a model for our function, the model of function around point x, which is the value of function plus quadratic model of phi with cubic regularization and linear model for G with this matrix A. And as the same as before, we know that this model is a global upper bound for our function. At the same time, it depends on a small number of components. It depends only on components which are in S. So if we pick a small number of components in S, then we can minimize this model effectively. So the method step is just a minimization of this model over the set, and the algorithm is pretty straightforward. So this is iteration scheme. In the beginning, we set starting point and some distribution from which we sample coordinates. Then on every iteration, we sample a number of coordinates, do a kind of line search to fit the parameter h, and just do the step of this minimization of this model. Okay, so what we can prove about this scheme? Because this is randomized algorithm, we want to get epsilon accuracy with high probability. And under general conditions which have been stated, we can prove 1 over epsilon complexity, which is similar to gradient descent complexity. Then we can introduce a special condition number, sigma, which is not a standard condition number. It depends on function g and on sampling distribution. But we have a lower bound for it using the standard condition number. Then we can prove that under the assumption that sigma is greater than 0, our algorithm has complexity 1 over square root of epsilon. So sigma is a kind of border between convergence of gradient descent and cubic Newton methods. And finally, under strongly convexity assumption, we can prove linear rate of convergence. So now let us look at some applications. We're going to solve empirical risk minimization problem, which is a sum of convex losses with linear predictors, and we add regularizer here. And we see that this function looks similar to our framework, so we have a huge sum here. The number of elements here is a number of data points, but it's not block separable, so we need to somehow fix this issue. And one option how we can do with that is what we call constraint problem reformulation. So we denote this inner product by additional variable. And we reformulate our problem as equivalent problem with new variables. But now we get the sum of separable twice differentiable components, differentiable regularizer, and simple set Q. And doing our framework, we can approximate these loss functions by second-order models with cubic regularization, treat G as quadratic function, and do these cubic steps. So here the example of comparison. First-order block coordinate method and second-order method for different block size. So block size is the number of components which we update every step. We compute how much time we need to solve the problem up to 10⁻⁶ accuracy. And we see that for medium size of blocks, second-order method outperforms first-order method. Thus, second-order information can potentially improve convergence rate of our algorithm. And another way how we can deal with empirical risk minimization problem is so-called notion of duality. So for convex optimization problem, there is known an object which is called a dual problem. Yes, we know that minimum of primal problem is lower bounded by the maximum of dual problem. And under some mild assumption, we know that they are, minimum of this equals to the maximum of dual. Then introducing the object, which is called Fenchel conjugate function, you can write down explicitly how the dual objective looks like. So this is the sum of conjugates of loss functions and conjugate of this regularizer. And now it directly fits our assumptions about block separability. So we can, again, tackle these components by second order models, 3G star with our first order model, and do this cubic step of iterations. And also it's noticeable that here we solve not the primal problem, but dual problem, and thus we get a kind of primal dual algorithm. So this more powerful method, and we can compare this method with another state-of-the-art primal dual algorithms, which are SDCA and SDNA methods, and we see that our method, which is green, outperforms these methods in terms of data access, number of data accesses. So as a conclusion, we have introduced new second order method, which is block coordinate. Thus, it updates only a small number of coordinates every step, and every iteration is cheap. And using this cubic regularization technique, we are able to prove global complexity result for this method. And solving dual problem of empirical risk minimization, we are getting a kind of primal dual algorithms which empirically outperforms state-of-the-art method of the same class. Thank you very much for listening, and if you have any question, I will be happy to answer.
Sorry, one question on you showed the first experiment on the primal and the second experiment on the dual. Which one would you choose? Or, for example, for logistic regression, but you showed a Poisson regression, could you solve both the primal or the dual with your method? And which one is preferred?
Well, it's a kind of still open question for me, because it's known that we can, for empirical risk minimization, we can apply stochastic gradient descent for primal problem, and we can apply dual, for the dual we can apply coordinate methods. And it's not clear what is the best approach in practice, but in our experiments, this primal dual approach, when we solve dual problem, it outperforms the primal methods. And one additional benefit is that when we have dual algorithm, we have for free the dual gap, which is an estimation for our accuracy, so we can control how much accuracy do we need for our problem. So yeah, dual approach is better from my side.
How about clock time? So you also have to choose a block size, which strongly affects the time to do one step. So.
Yeah, so one step of our method is actually a minimization of quadratic model plus cubic regularization. Yeah, and it depends. So the subsize of this subproblem, it depends on how many coordinates we choose. And the complexity is about number of coordinates per to the power of 3. So we need to choose the size of blocks such that we can solve this kind of linear system. And in experiments, about 50 to 200 or 200 is the best choice. So it's not reasonable to choose one coordinate for second order methods, but we need to balance between every step and the rate of convergence.
Thank you very much. Thanks again. we are actually 5 minutes ahead of schedule. If there are any more questions, but otherwise I suggest we move ahead. Okay, so we have 2 more talks of 10 minutes. So both talks will be on accelerated methods. The first one is going to be on accelerated greedy coordinate methods, and the talk is going to be given by Haihao Lu.
Okay, good afternoon. Thank you for coming to hear my talk. So I'm Haihao Lu, and I'm going to talk about accelerating greedy coordinate descent. This is a joint work with my supervisor, Rob Freund from MIT, and also Wahab Murakami from Google Research. So the problem we are looking at the problem. So it's very lucky that we have some extra time. Okay, so the problem we are looking at is a unconstrained convex problem. We are studying greedy coordinate descent. So actually, greedy coordinate descent is widely used in machine learning, even though people may not even know it. For example, in support vector machine, the fastest algorithm is greedy coordinate descent for the dual problem. And also, in boosting algorithm, you can view as boosting algorithm like a greedy coordinate descent. The goal of this work is trying to answer the question that when and how we are able to accelerate greedy coordinate descent. So we need some assumptions. We assume the objective function is L smooth. By that I mean this condition. It is like a coordinate-wise smoothness condition, which is used a lot in coordinate descent analysis. We will introduce 2 new notation, the L norm and L inverse norm. We will also need to introduce what is strongly convex. We define strongly convex with respect to the L norm. In other words, this mu is more like a condition number instead of strongly convex parameter. So this is the standard framework for accelerating greedy coordinate descent. So essentially, we keep track of 2 sequences, the X sequence and the Z sequence. We have a parameter sequence, theta I. In each iteration, we compute a linear combination of xk and zk, and we choose a coordinate jk1 by some rule, which I will explain later. Then we using a coordinate descent update to update the X sequence. and then we choose another coordinate JK2 by some other rule maybe, and then we compute a ZK, we update the ZK sequence by a coordinate descent update. So in the standard accelerated randomized coordinate descent, we choose a random coordinate here as a JK1, and we choose JK2 equal to JK1. So the accelerated randomized coordinate descent, or ARCD, is very well studied in the literature, and it has like a very cheap iterate cost, but it may require like more iteration to get a good convergence. Essentially, this is the convergence rate. You can have like convergence in expectation of the order 1 over k square. So there are like many good literature on coordinate descent method. One thing I want to mention in particular is this work, which will also be presented in ICML here. So there are some like very similar results between their work and the work I'm gonna present. Essentially, it's kind of like equivalent up to a linear transformation. So now let's talking about accelerated greedy coordinate descent, or AGCD. So the simple idea is that we choose a greedy coordinate JK1 to update the X sequence, and then we choose JK2 as the same as JK1. So this is like a very simple and standard idea if we want to do accelerated greedy coordinate descent. However, we didn't see any like study or any convergence result for AGCD. In fact, we suspect that there may be some counterexample where the accelerated rate may fail. I will like argue in next page on why this accelerated rate may fail in theory for AGCD. However, in practice, we always observe the accelerated rate. I will also argue that why we are able to observe this rate in practice. So essentially, in every accelerated method, the convergence rate is kind of like proved by defining a Lyapunov function, which have this formula. Here, this parameter sequence AK is at the level of k squared. So in the accelerated method proof, one would show that this energy function is decaying in iteration. Therefore, the optimality gap is decreasing with order 1 over k squared. So in greedy coordinate descent, actually greedy coordinate corresponding to the greedy coordinate for only the first term, but not for the energy function, because of the existence of the second term. And actually, because we do not know where is X star, it's maybe pretty hard to figure out which is the coordinate, which is the greedy coordinate for the decrease of this energy function. In other words, it's maybe like pretty hard to do accelerated greedy coordinate descent. But like this is like a condition. If this condition holds, then we are able to show that AGCD is gonna converge. This condition comes from like some back engineering of the proof. And if this condition holds, we are able to show that AGCD is gonna converge with this rate. And there is a parameter gamma in the condition. So in randomized coordinate descent, this gamma is gonna be 1. And in practice, we always observe that like this gamma is always smaller than 1. In other words, so accelerated AGCD is gonna have a better convergence rate than ARCD. So another option for accelerating greedy coordinate descent is ASCD. So essentially, the idea is that we choose the greedy coordinate to do the X update. But for the Z update, we're going to choose one random coordinate. That's why we call it semi-greedy coordinate descent. With this method, we are able to show that ASCD always converge with the same rate as ARCD. And why ASCD works in theory? At a high-level explanation, one can think that because we are using a greedy coordinate to do the x update, which corresponding to the first term in the energy function. And we use a randomized coordinate to perform the z update, which corresponding to the second term in the energy function. Therefore, in total, the coordinate is not a bad coordinate. And it guarantees a decreasing of the energy function. So we are also able to do accelerated semi-greedy coordinate descent for strong convex function. So the algorithm is slightly different, but it's quite standard. Here we still use the greedy coordinate to perform the x update, and we use a randomized coordinate to perform the z update. We are able to get accelerated linear convergence rate with order square root of mu. And remember that mu is a condition number, therefore this is the accelerated convergence rate. Now let me show you some numerical experiment. We did 2 numerical experiments. One is on linear regression with synthetic data because it's easy to control the condition number. The other is logistic regression with the data from libSVM, that is real data set. So here is the numerical results for linear regression. The x-axis is the running time for different algorithms. The y-axis is the optimality gap. Each column means different condition number. And the green line here is the ARCD, which is the benchmark. The blue line is the ASGD, which we have the convergence guarantee. And the green line is black line is the AGCD, which we have convergence guarantee only when the technical condition holds. We can see that in linear regression, ASCD and AGCD are always better than ARCD. And this is the numerical results for logistic regression. We can still see that the 2 new methods are better than ARCD. Especially the black line, which is AGCD, is sometimes perform much better. And why it performs much better? Actually, we compute the gamma value in the numerical test, and it can be we can see that the gamma value is always smaller than 1. Essentially, for a larger data set, the gamma is going to be much smaller. So it's kind of provide one explanation about why AGCD performs so well in practice. And also, the gamma value is going to be very stable after maybe 5,000 iterations. And essentially, that's it. So any question? No.
So I guess there's a little bit of overhead in finding the greediest coordinate, right? Is that dominated by the rest of the algorithm, so you don't pay much of a price for that?
Oh, yeah. So, yeah, I forgot to talk about that. So essentially, so this is the greedy coordinate essentially means the coordinate with largest absolute value of the gradient. But here, because we have a coordinate Lipschitz constant, so we rescale it by order 1 over square root of Li. So it's, yeah, here this term. So we compute the largest coordinate which has this, which is largest in this term. Yeah.
Is there another question? If not, let's thank Hailu again. So the last speaker of this session is Jelena again. So she's going to speak about accelerated methods under noise corrupted gradients.
Thank you. Okay, got it. Hi again. I am Jelena Diakonikolis. I will talk about acceleration with noise-corrupted gradients. This is joint work with Michael B. Cohen and Lorenzo Recchia. Michael unfortunately passed away last year, and the paper is dedicated to the memory of him. The setting of the paper is full gradient first-order convex optimization. The function, we will assume that it is smooth and possibly strongly convex. And it is minimized over a closed and convex region. Of course, there is a lot of history about first-order methods under various assumptions, including these ones. More recently, when it comes especially to smooth minimization, a lot of work has focused on, one, demystifying acceleration, and two, understanding how acceleration interacts with noise. So this work falls into the second category of understanding how acceleration interacts with noise. So I've mentioned noise. Let me tell you what we assume about the noise. So we assume that we have access to a first-order oracle to which, when we feed it a point from our feasible region, what we get in return is an inexact gradient that consists of the true gradient and some noise vector. We have instances of this problem in various applications. Things like this can happen because we may be estimating gradients from samples or from measurements, and sometimes noise is even intentionally added to the gradient to preserve the privacy of the data. The way we study this problem is by introducing a new accelerated method, which we call improved accelerated method, or AGD+. It is very closely related to other accelerated methods. In some sense, it generalizes Nesterov, but it improves over AXGD, which is another method that we had recently. Compared to Nesterov, it is more robust to noise. Compared to AXGD, it has lower oracle complexity. In some instances, it is equivalent to a lazy or a dual averaging counterpart of ACSA. But let me not get into too many details here. The analysis relies on the technique I have mentioned in my first talk at the beginning of the section. I won't go into all the details, except to just remind you that what we work with is an estimate of the true optimality gap, and we want to show that our rate, convergence rate times the gap, is a non-increasing function of time, modulo some small error, which would give us some standard guarantee that we see here. What happens in our analysis is actually what is, let's say, the most exciting part, is that when we perform the analysis, it allows us to decompose this error from each iteration into two parts. Now, the first part is completely independent of the noise. So we can do analysis as if there was no noise whatsoever. And the second part is exactly the error that we incur because our gradient was inexact. For smooth functions, the deterministic error we will get will just be 0. So we will just be reducing the gap. And the error due to the noise will take this special form. These little AIs, they contribute to our rate function. For accelerated methods, they are order I. Eta I, again, is a noise vector. And in the inner product, we also have some distance between the optimal point and one of the points produced by the method. There are various things you can conclude just from here by assuming different things about the noise. One immediate implication is that if the diameter of region is bounded, you can just apply Cauchy-Schwarz to this. What will happen is that the noise averages out. as long as its first moment is bounded, right? So in some sense, the bottom line is if you have a region that has a small diameter, noise accumulation will not happen. Another conclusion, and something that we knew actually both from theoretical and empirical observation, is that if we have smooth, non-strongly convex minimization over unconstrained domain, here noise starts accumulating. So our diameter here is unbounded, so the previous bound I showed you, it doesn't give us really anything. And this happens even if we assume some special things about the noise, for example, that it is zero mean and has bounded variance. And if we assume it is zero mean and has bounded variance, then we can get the expression we see there. So we'll have variance times these little AI squares over AK. Now, this would grow linearly with iteration count. For accelerated methods, AIs are order I, AK is order K squared, so the whole thing grows. One thing we can do in the analysis is try to balance out this term with what we get from the deterministic analysis that does not include noise. In that case, we would get what we call TOAGD+. It gives essentially theoretically optimal rates, and it gives the same rates as for ACSA. But there is another thing we can observe here, which actually will turn out to be slightly more useful in practice. So if we were to slow down our method and resort to something slower, where these little AIs were constant, which corresponds to convergence rate 1 over k, the error due to noise would just average out. It wouldn't be accumulating anymore. And if we switch to even slower steps, 1 over root k, we would get 1 over root k convergence rate, but our noise would also decrease at rate 1 over root k. And that's sort of an approach that we propose. You can apply this to the method I talked about. You can apply it to other accelerated methods. So what you do is you start with accelerated steps. You're running the accelerated method. Initially, noise is not really high, so it won't affect you much. Once the noise becomes unbearable, you restart and switch to a slower sequence, to this uniform sequence in the slower method. This sequence is guaranteed to average out the error due to noise. And then once again, when you see you're not making much progress, you restart again and slow down further to 1 over root k, which gives you 1 over root k convergence. The criterion for restart is something I won't get to talk about, but please ask me at the poster session. It has an interpretation of signal being dominated by noise. Now, let me show you a few numerical experiments, and here we assume that here we have added Gaussian noise with zero mean and epsilon standard deviation to the gradients. So the first set of experiments is for a hard instance for smooth minimization. On this instance, all the methods exhibit their worst case performance. I'm showing Nesterov's AGD in blue. AXGD is the earlier method we have, and AGD plus is the new method, which has lower oracle complexity than the previous one. I'm also showing gradient descent in green for comparison. Going left to right, noise increases. So the first column is noiseless. We have then moderate noise and high noise. And as we can see here, as we increase the noise, all the accelerated methods start accumulating the noise, and even more so if the noise is higher. Now, if we do either this restart and slow down or just use the optimized steps, when there is no noise, nothing should happen, and nothing happens. This is just sanity check. When there is moderate noise, we see that all methods now actually are not accumulating, they're converging, but the ones that use restart and slow down are actually much faster than the ones that just optimize the steps. And we see even more improvement when the noise is higher. Now, you may say, okay, this is an instance we made up, and it's worst case instance, so maybe this is not true in practice. So we also did experiments on a real-world data set, epileptic seizure recognition. Here we did logistic regression. Same story. If we do nothing, we see that when we add more noise, all the methods accumulate the error. And when we do restart and slow down, first of all, sanity check, and then we see that all the methods stabilize, become convergent, and are actually better than optimizing the step sizes. So to summarize, I talked about a new accelerated method that has a very simple analysis that allows us to understand how acceleration and noise interact. And we also had a restart and slowdown approach that can stabilize the error. So for this restart and slowdown to work, I assume that we know the noise variance. In some cases, this is a realistic assumption. In others, it's not. So I would be interested to see if there is a way to get something similar when we don't know the noise variance. Thank you. Please come to my poster. I should just make a quick notice. I have posters 220 and 67. So if I'm not at one of them, I'm at the other. But yeah, please come and talk to me. Thank you.
Thank you for the nice talk. Are there any questions? So if not, I'd like to thank all the speakers of this two very nice session and have a nice coffee break.
Yeah.